I won't waste too much more time on it. If it doesn't work, it doesn't work. Look at that. Maybe it works. All right. So, add them up. If opposite directions subtract. I mean, I'm going to put that here, but we should hopefully know that. So, for example, if one is into the page and one is out of the page, you have to define one of them as a negative, one of them as a positive. I don't care which. Call out of the page as positive, call into the page as negative, if you really want. So, for example, into the page we'll say is negative, out of the page we'll say is positive. I'm not going to even put that there. If opposite directions subtract. Classic vector math. You've been doing a lot of that at this point. And this did remind me of something that I'm going to go ahead and put right now. I'm actually going to put it down here. You do not have to add this. It may seem a little silly, but I think it's important to clarify because we get a lot of questions on this. You will not see a north, south, east, west problem. Not going to happen. The terminology I will use is up, down, right, left, into the page, and out of the page. Those are the terminologies out of the page. So on the test, again, it's unfortunate that we have to work in 3 dimensions because 3 dimensions is hard when I give you a 2-dimensional paper, but it is what it is. We have to. If I say something's traveling to the left, it's traveling that way. If I say to the right, it's that way. If I say up, that does not mean out of your paper. That means, where's my carpet? There we go. If this is your beautiful test, up is the top of the paper. Down is the bottom of the paper. Out of the page is out of the page into the page. It sounds silly, but please, that's going to be a class. If you mix up those directions, it doesn't matter how good you are at it. You're working with bad ingredients. So, yeah.
When we're doing right-hand rule, let's say my thumb is facing me, then out of the page.
Yes. If your thumb points out of it, and you all can kind of, it depends how you want it. If you have your paper kind of flat on the desk, you can kind of put your hand over the paper. And if your thumb points away from the paper, that would be out of the paper. If you're holding, you kind of have to have a reference, where's your paper located? If you're like holding the paper up in the air, then a thumb towards you would be out of it. Yeah. Whereas if you're sitting and your paper is flat, and I do right-hand rule, my thumb points towards me, in that case it would be down. So it all depends how you're referencing the paper. So my recommendation is when you're doing right-hand rule, do it with respect to your paper. Make your fingers line up with the direction of the arrows in the paper. I may not give you arrows. I may say it's going to the left in a magnetic field that's pointed into the page. Draw some arrows. Draw some arrows on your paper. Remember, drawing a picture is step 0 in solving these problems. And the key there, have your paper, I generally recommend have your paper flat, line up your hands with the arrows on the paper. Makes life a little easier. All right, so right-hand rule number 2. Is this working again? Hey, look at that, 2 streams. Whoa. All right, right-hand rule number 2. We're going to draw my beautiful hand. Ugh. There it is. Oh, it's hideous. All right, your thumb is in the direction of the current. Your fingers are towards P, point P. Maybe I don't label it as point P, but hopefully you got the idea that point P is the point you care about, where you're finding the field. So towards where you're finding the field. I just call that point P because that's what we've been using. Towards point P, where you're finding the field, and your palm, thumb in the direction of it, fingers towards point P, your palm points in the direction of the field. You can swing your fingers 90 degrees, both things work the same. Your hand will point in the direction of P. Your palm will. I've been showing you all where you swing your fingers towards it. So let's just quickly show an example. Here's a wire, there's a current, there's point P, find the field at point P. Fingers in the thumb in the direction of current, fingers towards point P, palm points out of the page. Magnetic field points out. Thumb, fingers, palm. You know what? To make my... I'm going to redraw this just so it matches the hand, because that's kind of nice. Let's have my current be going in the direction that is shown there. Let's have my point P over here. And use... I drew a left hand. Let's redraw my hand. You're this in the back of the hand or the front of the hand. Let's make that actually a right hand. And it matches the picture. E. There's my fudgy fingers. All right. Oh, no, it's okay. Sorry. My hand was good before. Thank goodness this is digital. Woo. All right. Your palm points towards it. The unfortunate part is your palm. It's on the other side, so it's fine. Whatever. Into the page. Thumb in the direction of current. Fingers towards point P. You can swing it 90 degrees if you want, or just use your palm. Pick your poison. Thumb, P. Points into the page. Thumb, P. Into the page. Alright, I'll write it out in words. Thumb in direction of current, which is I. Fingers towards point where you want field. You want to find field. Palm gives direction of field. Beautiful. Palm gives direction of field. Thumb, fingers towards it. There you go. And again, this is actually taking inspiration from another student, the way they wrote it. I like this, so. Even with my terribly drawn hand, it's better than nothing, I think. Okay, so I promise you, this is a non-efficient use of space. You will 100% be able to fit everything on your note card. We only have one last thing to talk about, which is Faraday's law and Lenz's law to fit on here. And I believe we will have time to basically just do a heck of a lot of right-hand rule at the end of the class. All the right-hand rule. Okay, so I'm just pausing here because I want to make certain everyone got everything before I switch and it's all gone for a temporary amount of time. Yes.
So when we're trying to find force, we're using the right hand rule number 1.
Yes.
When we're trying to find magnetic field, it's number 2.
Yes. Yes. And let me actually add that here. I think that's a great point that I can put here. Finding B due to I. There we go. We'll put that on there. I think I put that on the last one. Let's see. Nope. Well, don't have room. Maybe I'll try to fit it in there later. Right-hand rule 2 is for finding B. Right-hand rule 1 is for finding F. Yes, that's a great point. And those are really the only right-hand rules. Yes, there's right-hand rule 2.5, which thankfully is the easiest one. And it's not technically necessary, but yeah, it is kind of hard to do without it. So, Faraday's law, last section. Faraday's law. Faraday's law says you generate a voltage, we call it an EMF, if you have a changing flux. So, we first introduced the idea of flux, we've seen this before, BA cosine theta. Theta is the angle between B and A. A is the area vector. And then we said we get a voltage, which is equal to negative N, if we have a bunch of loops, times the change in magnetic flux over the change in time. And to kind of just shove that equation, shove that in there, the change in BA cosine theta over the change in time. N was the number of loops. A is area. I think that one's pretty straightforward. If you want, add what each of these variables means if you're uncertain or you think you'll forget or anything like that. If the loop is square, area is length times width. If the loop is a circle, it's pi r squared. If the loop is an octagon, that would be awful and I wouldn't do that to you. So, either a square or a circle. No triangles, no parallelograms. Yeah. Yeah. Area, if square, length times width. If circle, pi r squared. Yep. That's a good question. If at any point you will have a question, please ask me, because a good rule of thumb is we have enough people here that if one person has a question, several people have the same question. Generally true. And several is enough for me to write something down. So. All right, so speaking of changing flux, Lenz's law is going to be a bunch of words. There's no really quick way, there's no nice picture I can draw that'll explain it all. So I'm just going to start writing Lenz's law in a bunch of words, and you can decide how much of this you want to put down on your note card. Lenz's law, basically summarized, loop will generate current to oppose change in flux. This is literally, I don't know if you Googled it, if it would need this exact definition, but that's as simple. It will generate a current to oppose the change in flux, aka it will, you know what, I'm going to even use a different word than flux. Change in number of field lines. Because I think that is more clear, and that's literally all flux is. How many field lines go through it? Am I getting more? Am I getting less? Yeah.
Is that why n is negative?
Yes. That's where that negative comes from. Good news, you all know we're in the test. Will there be a negative voltage or a positive voltage? Same thing I told you all before. So I put this negative because, yes, this connects to Lenz's law. The negative is saying I generate a voltage, which will generate a current to oppose that change in flux. Yes. That's why we kept that negative in there, even though it didn't change any of our, like I never had negative or positive answers. It's because it connects conceptually, oppose the change in flux, which is just the number of field lines. So, how do you do this? First step, identify direction of existing B, of existing magnetic fields. Identify direction of existing B. Step 2, am I getting more or less of those? Wow, that's, yep, there we go. Am I getting more or less of those lines? Arrows? Lines? I'm going to write the word field lines. Then I don't have to be finicky. Well, I say I'm going to do that. Google Slides says no. Oh, this isn't Google Slides. PowerPoint says no. So find the direction of the existing field. Figure out whether or not you're getting more or less of those. Yep, just lines. Generate a magnetic field to counter the change. Oh no, I made a type. Devastating. Go eraser. Don't go eraser. Well, we're going to have a really big N. Counter change. Step 4, use right-hand rule 2.5 to find direction of current. Okay. Am I getting more field lines into the page? Am I getting less field lines into the page? Am I getting more field lines out of the page? Am I getting less field lines out of the page? We'll do it again. We'll have time at the end of class today to do a few examples. Once you get this down, in my opinion, this is one of the easiest things, but it's just making it click. Just making it click, visualizing a bunch of arrows. And visualizing, I'm getting more arrows. Oh, I'm getting less arrows. I want the opposite of that. All right, what is right-hand rule 2.5? I technically have one more thing I need to fit on here. I'm going to save this and reopen it so I can actually use my eraser. So, the reason these technical difficulties come up, not that it really matters, but it gives me excuse. For whatever reason, whenever you write in a PowerPoint slide, it uses... I'll be back up, don't worry. Whenever you write on it, some reason it's hard for it to save those files. If you ever look at the difference between my PowerPoints without writing and my PowerPoints with writing, it's bigger, significantly, storage-wise. It's not very efficient at saving it, but it's the best I've found as far as doing this kind of stuff. So at some point, once I get a lot of writing, it gets really angry with me and doesn't like it. Wow, nice, it's all gone. Whatever, I'll rewrite it real quick. Identify direction of existing B. Am I getting more or less field lines? Generate B to counter change. And step 4, use right hand rule 2.5 to find direction of current. Okay. Because I have space, I'm going to take all of this and move it down because I need just a couple more things. I'm going to put right hand rule 2.5 up here. Oh, that's going to be hideous. All right, your thumb goes in the direction of current. There's a thumb, and then your fingers, oh, there they are. Ooh, that's not bad. Wow, look at that. That's the best one. Your thumb is in the direction of B, and your fingers curl in direction of the current. Oh, it's so good. It's not great, but it's fun. So, again, give myself a little bit more space. Good news, I'm not going to ask you to draw a hand on the test. Thumb in direction of B, fingers curl in direction of current. Okay. The last thing, the reason that, yeah.
Is that thumb in direction of the original B or the...
Whatever B there is or you want to make. Yeah. So in this case, this rule says if I have a current going this way, I make a field this way. If I want to make a field this way, then I need a current that way. So this right here rule just says if I have a loop of wire with some current going this direction, it will make a field this way. So it will not tell you, Lenz's law is more complicated than just, oh, what's the direction of the existing field, curl your fingers, there's the current. There's a few more steps. This one just says, if I have a current, if I want to make a field this way, I need a current this way. Or if I have a current this way, it makes a field this way. Go either direction. So if I have a field, if I'm like, I have a loop, and I want a magnetic field up, which way should my current go? Point your thumb up, fingers give you the direction of the current that way. I want a magnetic field down. Which way should I have my current go? Thumb down, fingers that way. Oh, I have a current carrying wire that's going clockwise. Fingers go clockwise, thumb gives you the direction of the field. So this just says if I have a loop. So the right-hand rule number 2, finding B due to I in loop, or vice versa. All right-hand rule 2 does is find the magnetic field due to a current in a loop, or vice versa. Finding the direction of current if I want a field. We'll do some examples of Faraday's law. We'll probably sit that one the most. Last thing I need to give you all is we had the situation with we had the problem where we had like a rail and we had something moving to the right with some velocity, and it said find the EMF generated, BLV. L is the length of that loop, not the length of the loop, the length of the rod that's moving. And this also was literally just a rod flying through space. It's the same thing. This equation goes to both of these. If you have a rod flying through space, BLV. If that rod's connected to a loop, great, BLV. If that rod's not connected to a loop, great, BLV. This tells you the voltage generated by a rod moving. It does not tell you which way current flows. It does not tell you which way current flows. It only tells you, here's the voltage. If you want to get current, and you know the resistance, you know what, let's draw a little resistor here. V equals IR. Okay, there's a problem like that. If I give you a resistor in it, and you want to find the current, you know what, we'll make it explicit. Epsilon equals IR. Epsilon's just voltage. V equals IR. So if you want the current, bam. I'll make it explicit in very tiny letters. So there you all go. This is everything you need to know. We will literally spend the last 25 minutes of class doing a heck of a lot of right-hand rule. Just going to throw out example after example, chuck it to the end of these slides. I won't tell you which one we're doing until I give you the answer. Because you need to be confident. Well, you don't have to be confident. You need to be able to go back and forth between these rules. Oh, I use this one for this problem, or this one for this one, or this one for that, whatever, so on and so forth. But since Faraday's law was the most recent one, we will start off with an example of that. I'll make it explicit that we're going to start with an example of that. All right, so I have a loop of wire entering a magnetic field pointed into the page. Find the direction of current. Loop of wire entering a magnetic field pointed into the page. Find the direction of current. This is Lenz's law. I'll kind of walk us through this. As it's entering, imagine a little bit later. I am now. Did I get more field lines or did I get less field lines? More. Which way do those field lines generate? Which way are those pointed? Into the page or out of the page? Into. Do I want them? No, I don't want them. So, if I'm getting more into the page, how do I counteract that? Out of the page. So I'll make this explicit. Getting more into page. Getting more what? Getting more B. More B into page. Generate B out of page. to counter this. So I'm going to generate a magnetic field into the page to counter this. Which way is the current that makes that happen? Right-hand rule 2.5 shows to make B out of page, that's what counters it, current goes blank. So this is the thought process written out in words. I'm getting more into the page, don't want it. Makes it out of the page. Which way my finger curl? Counterclockwise. That's the logic for Lenz's law. Counterclockwise. I'll write it out one time, even though it's a big word. Counterclockwise. I'm getting more B into the page, don't want it. Generate B out of page to counter it. Right-hand rule shows to make B out of page. Current goes clockwise. Let's do this one, where I start in the field and I'm exiting it. So that's original. A little bit later, I'm not going to draw the little bit later on the problems. In the problems, I'll literally just give you this and say find the answer. But I'm drawing kind of both the before and after to help you kind of visualize this is how you should think about it. It's going to move a little bit out of it. Same question. Am I getting more field or less field? Less. What am I getting less of? Into the page or out of the page? I'm getting less into the page, so I need to make more into the page. Oh, and I'll put here, this one was counterclockwise. So, how do I make a field into the page? Put your thumb into the page. It generates a clockwise current. It's the opposite. Again, like most right-hand rule problems, y'all, the only way to really get this down is to practice, practice, practice. But I wanted to kind of walk through the steps. I will write this last one out, and this last one I'm going to write this much for just because it takes a bunch of time. Getting less B into page, generate B into page to counter this. Right-hand rule 2.5 shows I clockwise to make B into page. So that is the thought process. That is the logic. Check this out. Yeah.
Will you ever give us a question where B will be moving left or right and B will come in and out of page? Or will it always be B moving up, down, left, or right?
B will pretty much always be moving up, down, left, or right, just because I can't draw. Yeah, I won't try to be tricky and say the loop's moving into or out of, just because I'm giving you ones like that. In that case, it actually wouldn't make a current. If this B was magnetic, it was uniform everywhere. That's a good point. No, I'm not going to give you where the loop's going into and out of the page because that's also just confusing wording-wise. Yeah?
So, rule 1 force, rule 2 magnetic field, and rule 3 current, or 2.5 current?
Rule 2.5 is first a loop. Magnetic field due to a loop. Yep. It's basically just, the reason I call it 2.5 is rule 2 is finding the magnetic field due to any wire. Rule 2.5 is, okay, just for a loop you can do this.
That's the differentiation, just a loop.
Yeah, it's like a specific case of the, yeah, that's why I call it 2.5. It's like a specific case of that rule. Yep. Yeah.
So on this one, can you like do it with your hand again and kind of explain it?
Yeah, I'd be happy to. So here it's leaving a magnetic, so this magnetic field is into the page. As it leaves it, I'm losing those field lines. So then I need to make more of them because I want to lose them. So I need to make them into the page. So how do I make them into the page? I put my thumb into the page and my fingers. You're using right-hand rule 2.5 to make the field. You're like, oh, I need to make this field. So when you are solving this problem, you only use right-hand rule 2.5 at the very end. When you said, I need a field in this direction. How do I make that field? Put your thumb in that direction and your fingers give you which way the current will flow. So everything leading up to the last step, you don't use your hands at all. The last step is once you've said, I need a field in this direction to counter the change, then use right-hand rule 2.5 to make that happen. You say, I need a field into the page, bam. Thumb into the page, current will be clockwise to make that happen. Yep, does that help? Clarify that? All right, let's do a few more right-hand rule ones. This is just going to be hodgepodge mixed up. I'm not going to tell you which right-hand rule until I solve it in front of you. So I'll have you all try it for yourselves. Negative charge moving down in a magnetic field into the page. Find the force. Negative charge moving down, magnetic field into the page. Find the force. So this is right-hand rule 1. Right-hand rule 1 says put your fingers in the direction of B. Put your palm in the direction of B. So your fingers point down, your palm is into the page, which, again, for my screen, I'm going to show I'll show you all class and then I'll show it. So fingers down, B into the page, my thumb points to the left. If you say left, it's wrong because it's a negative charge, and then the force is the other direction. So, remember, be very careful with these negative charges. Down, right, but it'll actually be left. Sorry, left was the right answer, right? I don't know what I just said. Either way, it gets mixed up because my screen is opposite orientation of yours. So, the force is to the left. A force on a positive charge would be to the right. I will literally draw the exact same picture, but with a positive charge, and the answer will be the other way, just to make this abundantly clear. The force in a positive charge will be to the right, just to show you their opposites. Okay. Now I'm going to do a word problem. Current goes up. Find direction of B to right of wire. I will straight up tell you all, there is not many pictures on the test. You have to draw your own. DIY. One, pictures take a while to draw, or they take up a lot of space, so I don't draw them on there because of that. I say take a lot of space. Makes it hard to fit everything in, but more importantly, you need to be able to take words and make a picture of it because in the real world, that's pretty much how everything works. There's a verbal description of what's going on. It's very often, you can't see moving charges. So, you can't see magnetic fields. You'd have a sensor that measures these things. So first step is just drawing the picture. If you drew your picture like this, you did good. That's the first step. Next step is using the right-hand rule. So right-hand rule 2 says thumb goes in the direction of current, finger goes towards point P, the point you care about. Palm points in the direction of the field there. Palm points into the page. So there's a line, thumb is the direction of current, P is to the right, palm points there, thumb in the direction of current, palm points into the page. And I'll be honest, y'all, when I'm drawing these into the pages, I have to do a little bit of thinking whether it's an X or an I. So take your time. It's really easy to mix these things up. The good news is all my answers are into, out of, whatever. But yeah, please don't mix up what the X's and I's are. And remember the trick to that is think of an arrow that you like shoot out of a bow. You see the feathers on the back. If it's going into the page, you see the point of it coming at you if it's coming at you. That is, I still use that technique to this day because my memory sucks. All right. So there's two problems. Let's separate them by some purple stuff. No, that's going to be really ugly. All right. Another one. Positive charge. Ooh. You know what? Let's do this one. Loop is moving to... no. These ones are too hard to write in words. I'm just going to draw a picture of it. All right, I have a loop going this way. Here's some magnetic field lines. Find direction of I. So thinking through the steps, this is a Lenz's law problem. Am I getting more field lines or less? Less. What way am I getting less field lines of? Am I getting less of them into the page or less of them out of the page? Getting less B out of page. Make B out of page. We'll call those orange, so I'm going to make some. Right hand rule, 2.5, counterclockwise current. To make a current that is going to make a field into the page or out of the page, right hand rule 2.5. So I was losing dots. I need more dots. How do I make more dots? Well, first I just draw ahead and get more dots. Great. Now that I know that, I move to right hand rule 2.5 and put my thumb that way. My current will be counterclockwise to make that happen. So again, the first few steps have no right hand rule 2.5 at all. It's just what way do I need to make more field lines? Which way do they need to be to counteract the change? I do need to make more. I need to make more out of the page. Bam. Get that counterclockwise current. I need more out of the page. Bam. Like that. So that's the key to succeeding on these. Do not use your hand until you've identified, I need field lines in this direction to be happy, to be fulfilled, and whatever else. All right. Towards that end, I've got a rod. Zoom in to the right. Find direction. You know what? Let's go the other way. Find direction of I. So there's a field everywhere. All over the place, but the thing is moving that way. Go through the steps. Yes.
Does it matter how far to the left it's moving?
It does not. That's a good question. Does it matter how far to the left it's moving? It does not. All that matters is that it is moving to the left. Remember our equation for the voltage it generates is B, which is the magnetic field, times the length of that rod, times how fast it's moving. So that's a good question. It only matters how fast it's moving, how big that rod is, and how strong the field is. So I'm going to draw the same picture. And this is a strategy you all can use. I'm going to draw the picture just a little bit later. Did I get more field lines or less in my enclosed loop? In my enclosed area? And this is the key, you all. This is my enclosed area. This is the only loop part. The rest of this is open. We don't care about open things. We only care about closed loops. Here are my closed things. I have less. I have less field lines into the page. So I need to make more field lines into the page. So I'm going to make some more. How do I make magnetic field lines into the page that way? Put your thumb in. Current's going to go clockwise. Thumb in, clockwise. Thumb in. Yeah, clockwise. What color do we want? Oh, a nice pink. Current will go clockwise. Make certain you all can recognize. The key here is seeing where the closed loop is and making that happen. All right. Last one I'm going to do with you all. Combo. Here's a wire. Here's a loop. Should I add these or should I subtract them? If I'm finding the field at point P due to both of these together, should I add them or should I subtract them? That's the question to you. Find the field. 2 for 1 special. Find the field due to both of these. Call that I1. Call that I2. You need to be able to find the fields due to multiple wires and combine them together. That is a key skill you all need. So breaking this into pieces, wire 1. Wire 1, we do classic right-hand rule 2. Put our thumb in the direction of the current, we put our fingers towards point P, our palm points out of the page. So B1 is out of the page. Thumb points in the direction of current, fingers towards point P, palm is there. Thumb in the direction of current, fingers towards point P. Current is out of the page due to current 1. Let's make it pink. That's exciting, right? So that's B1. Current 2, you have choices. You can use right-hand rule 2 for this. Right-hand rule 2 works for a loop as well. Just pick literally any spot on that loop. Let's pick the bottom part. Current is going to the right, fingers towards point P. It's also out of the page. You know what? Let's pick the right side of the loop. Current's going up. Current's over here. Out of the page still. Doesn't matter where you pick. Or you can use right-hand rule 2.5 and just circle your fingers around and thumb points out of the page. So current 2 is also out of the page. So do I add these or subtract them? Same direction or opposite? Same, so they add. They add because they're in the same direction. Ideally, I would put both of those dots on point P, but I can't put both of them on top of each other without it being unclear. So just know that that's a limitation here. Then if you had the math, you would have the dimensions, and you would calculate the fields to both, and you would add them. I will quickly just show the opposite case for... I will literally take the same problem, and I will just change one thing about it. If I have a wire going the other way, and I have a loop with the current going the same way, I'm going to let you all find for yourself well, that the magnetic field 1 now points into the page, and the magnetic field due to the loop still points out of the page. I2, I1. And so then they would subtract. So we defined out of the page as positive, so we'll say negative B1 plus B2. Negative. So there you go. Because they're opposite directions. So now one's a negative, one's a positive. All right. Feel free to come up, ask any questions. I'll happily stay as long as necessary. If you have any questions, please email me. I will be checking my email fairly frequently. I know the test is coming up, so I check it even more frequently than normal. If you send me questions, I will do my best to answer them as clear as possible. If my explanation sucks, ask more questions and I'll try to do better. But please, please, please email me, ask questions, look things online, practice. Make certain you bring your note card. If you don't have it, you'll just have to use the formula sheet. It's not the worst thing in the world, but definitely not the best. All right, let me